Hello, this is Malek Al-mallah and my colleague Abdulghani Al. Today we are going to present our final design project in the Advanced Embedded System Design class under the supervision of Professor Bilal Sabah. Our project is mainly about autonomous driving. This topic, autonomous driving, is a fast-growing and new field in the industry. It's all about reaching level 5 of automation, and which means a fully self-driving car. Of course, this will bring a lot of benefits to our life as a human being due to the fact that it will reduce human error and the human imperfection in the driving, which will lead to optimize our transportation time and make us make use of our driving time and increase our productivity. Due to these many benefits, a lot of car manufacturer and the high-tech companies are investing a lot of money and billions of dollars on the research in this field. This field, by its nature, is a robotics field, and it's a multidisciplinary field, which means the problem is multi-layered, and each layer need a specialized people in many different areas. From our project perspective, we are going to focus on the low-level controller, which take the trajectory. In other words, the high-level motion planner will take the perception and the environment in his consideration to detect a very exact trajectory or a set of points at which we have a certain speed and direction for the car. After the motion planner decide this trajectory, it will send it to the low-level controller. The low-level controller, on the other hand, in itself has two actually different perspectives. The lateral control, with which we control the angle of the steering, and the lateral control with which we control the speed or the displacement of the vehicle. Now, each one of these controllers actually have many different algorithms depending on the driving situation. And in this project, we are going to focus just on longitudinal control to scale down our problem. The longitudinal control, or one type of the longitudinal control, is the adaptive cruise control, which happens most often in the highway driving, where the high-level motion planner decide to follow a certain car as a reference. In this situation, the low-level controller needs to follow this car reference and keep a safe distance and maintain the car speed according to this reference car.
Okay, hello everyone. This is Abdulghani Jundi. We have to answer this question. What is adaptive cruise control? Adaptive cruise control is a cruise control with another feature, which is keeping a distance between the vehicle and the ahead vehicle. The driver can choose the distance, the desired distance, so that the two vehicles are apart from each other. Next. Here we have the car prototype with all the components. As we can see, we have two microcontrollers are used, which are Arduino Mega and HCS12. They are serially connected for communication. And also we have a 9-volt battery to power the H-bridge, which used to drive the motors. Also, we have an ultrasonic sensor. Next, okay. Here we have the electrical design. As we can see here, As mentioned previously, HCS12 and Arduino Mega are serially connected for communication or serial communication. The HCS12 obtained the data from the ultrasonic for further calculation, specifically to calculate the distance from the vehicle and the object. The ultrasonic has 4 pins, which are ground, VCC, echo, and trigger. The trig pin could be triggered by pulse width modulation provided by HCS12, while echo pin is used to send data to the HCS12 to calculate the distance. Then the HCS12 will update the Arduino with this distance every 40 milliseconds using real-time interrupt, as will be seen later. Also, we have here 9-volt battery voltage regulator. The 9-voltage battery will be stepped down using the voltage regulator to power up the Arduino Mega and HCS12. Also, the battery will power the H-bridge. The H-bridge is a very important component in this design because it controls both speed and direction of the vehicle for both DC motors. The speed is controlled using pulse width modulation, and there are 4 wires connected from H-bridge to Arduino, which are pin 50, pin 51, pin 52, pin 53 for direction control. This direction control emulates the electrical braking system, while the speed control ensure the fastest speed profile could be obtained. Next.
And now let's go to the details. I'm going to show you now the HCS12 algorithm. At the start, after the bar has reached the HCS12, the HCS12 will start by raising the TCNC overflow interrupt to the highest priority among all the maskable interrupts. The reason for this step will be explained in a few moments later. Then we are going to enable all interrupts. Of course, we can't set the priority after enabling the interrupt, so we have to set the priority before enable any interrupt. Then we are going to initialize the PLL and the several functions in the HCS12. Then we are going to initialize the pulse width modulation, with which we trigger the ultrasonic and get the distance from it. The pulse width modulation is done by the hardware of the HCS12 and will need no more attention after this step from our code. Then, after we enter the main loop, all what the main loop is doing is just to check the flag, which is a variable we have declared, is to check the flag. If its sign is still the same, it will do nothing. But if the sign is changed, then the Arduino updater will be called. Of course, the sign of this flag will be changed using the real-time interrupt. Now, while waiting in the main loop, if a rising edge has happened at the IC0 pin, then an interrupt will be detected and the handler will be called. Then inside the handler will check if the detected event is a rising edge or a falling edge. If a rising edge, then it will save the TCNT and it will clear a variable called TCNT overflow count. Using this variable, which is TCNT overflow counter, we are going to see how many times does the TCNT overflow while we are waiting for the next event, which is the falling edge. If the falling edge has arrived, we are going to save the TCNT once again and update the distance according to the TCNT register, which is we saved at the rising edge and the falling edge, and the TCNT overflow count. Of course, with wherever we are, if we have a TCNT overflow, then the TCNT overflow counter will be increased by 1 using the TCNT overflow interrupt handler. Now, why did we increase the priority for the TCNT overflow? Well, assume we have the case where the rising edge has been detected and the TCNT has been detected as well at the very same moment. Then the controller will go to the TCNT overflow register and increase the counter by 1. But after we call the IC, the IC will set the TCNT counter back to 0, which means it will cancel the effect of the fact of handling the TCNT overflow register first. But if the case is when we have a falling edge, we need our HCS12 to increase the TCNT overflow counter by 1. So we will not be wasting entire TCNT counting cycle. And then the controller will call the IC handler and use the TCNT value and the overflow counts and the overflow number to update the distance. This whole process of updating the distance is completely separate of updating the Arduino. Updating the Arduino will happen based on the real-time interrupt, which is each 40 milliseconds approximately. Now, why we didn't update the Arduino within the RTI interrupt handler? Well, simply because we don't want us to spend a lot of time saving the RTI while there is an IC waiting for us to save the exact TCNT value. In this case, we will be losing our accuracy with saving the TCNT register. So all what we need is to save the RTI as fast as possible and updating the Arduino with as much time as we need using the main loop. So we are available within the main loop and while we are updating the Arduino for any interrupt to ensure accurate measurement. Of course, this will cause us to update the Arduino in non-regular time in some cases, but this is fine for us because this 40 millisecond is in fact has a lot of margin.
Okay, now let's talk about Arduino rule, which was programmed using MATLAB Simulink. As we can see here, we have a receive block, receive the data from HCS12 every 40 milliseconds, and then will trigger a subsystem called signal conditioning and error calculation. The error will be obtained from the subsystem to the BID controller. Now, signal conditioning block and BID controller will be demonstrated in a minute. Let's take now the output of the BID block. As we can see, it will be divided into 2 branches. The first one, as we can see here above, is the magnitude. We talk about from minus 255 to 255. Magnitude block will take the positive value and send them to the pulse width modulation of the DC motors to control the speed accordingly. The other branch takes action whenever the polarity change. As we can see here, this sign plug, if this sign plug receives any positive number, it will consider it as 1, while if it receives any negative number, it will consider it as -1. In this case, it will control the direction of the DC motors and change the polarity when needed to emulate an electrical braking system.
Okay, now let's dig into the signal processing block, which is a triggered subsystem. Now, the main function for this block is to do some DSP filtering for the received signal from the HTC12 and set an acceptable steady state error, which in our case is 2 centimeters. Now, let's start by discussing the DSP filtering. What we have here is we are going to check the current sample and the previous 3 samples and take the most frequent element in this array. And if we don't have a most frequent element, in case we have 2 elements with the same number of, in case we have, for example, 4 samples, all of them are different. In this case, the mode function will take the lowest sample. Of course, the initial condition for these delays is the reference distance. So we will not have an undesirable car movement at the start of the system. Sorry. Okay, the second part is to ensure that we have just a 2 centimeter steady state error. So if the error is below 2 centimeters, then a 0 will be sent to the BID controller.
Okay, we have mentioned many times that we update the Arduino every 40 milliseconds. From where this number, we obtain this number. So let's talk about that. The time TP taken by the car to reach 63% of the transition is 0.68. We take the car prototype and make it away from the target by 1 meter, and then measure the time needed to reach 63% of that target. After that, we multiply this time by 0.1 to obtain the maximum value of the update Arduino time, and we choose to be 0.04096 seconds, or simply 40.96 milliseconds.
Okay, now let's talk about how did we tune our BID controller. We, of course, use the Ziegler-Nicholas method. In the first step, we set the integral and differential gain to 0, and we kept increasing the proportional gain until we reach the ultimate gain with which the car will move as shown here in this video in a sinusoidal wave. Using this sinusoidal wave, we calculated the ultimate time, where we calculate the whole interval and the number of cycles, and then we divided the interval on the number of cycles. The first result from the Ziegler-Nicholas method is shown here, which was kind of not what we want. A lot of overshoot and long settling time. So we did many steps, and we picked these 4. As shown here, we reached this result here, where we have just a simple and tiny overshoot and then a steady state achieved. That's it. Thank you all for watching.